Okay, let me just first close the door. And we're ready to go. Okay, so as we have seen, here we are describing basically a very simple mechanism that we have already presented, which is a slider crank mechanism which is typically used to transform rotary motion into linear motion of the mass. We have 4 bodies, which have been already highlighted. And in particular, we have made a series of hypotheses. All of the bodies are rigid with the exception of body number 3, which is deformable. And we have all the parameters, the material and the geometrical parameters that we need to further develop the exercise. In particular, the very first step that we have to do, given that we want this body number 3 to be deformable, is to assign a physics. Okay? This is up to us. There is no constraint in that. For the sake of simplicity, we just adopted the most simple physics model that we have, which is the 1D Euler beam. Okay? Both for basically axial behavior and the flexural behavior. So these 2 equations that you should be familiar with are just these 2 equations that regulate, that govern the axial and the flexural behavior of the beam in absence of distributed loads along the axis. Okay, and the idea is to basically derive as first goal the shape matrix, the shape function matrix psi for the body number 3. In so doing, we basically assume a polynomial expansion for the displacement induced by the deformation, u over bar. I'm just going to recap a little bit. And we saw that proceeding like this, we needed basically to determine 6 coefficients. Okay, 6 coefficients that, if we assume every point in our beam to have basically 3 different deformation parameters, Q1, Q2, and Q3, for example, here, it means that we need at least, in order to determine the 6 coefficients, to know the solutions at 2 points. Okay, so we have 6, as you can see, deformation parameters at hand. These 2 points are what we typically call, even typically in the finite element approach, nodes. Okay, these are 2 nodes. And so here we basically, what we do is basically, based on the knowledge of the solution at these 2 points or nodes, we interpolate the solution using the shape functions, so to get the displacement induced by deformation all over our body. That's basically the reasoning behind all of our operations here. And to do so, we need to determine, as I was mentioning, the matrix of shape functions. We went through all of this. We were able to determine the coefficient based on the 6 coordinates based on deformations. And we were able, writing in matrix form, this matrix. But this matrix here, we wrote it with an overhead. So it's not really what we were looking for. Why? Because the one that we look for is the one without this so-called hat. Okay, but what do we want to denote with this hat? Why do we have hat here and here? What is it that we actually seek when we want to basically derive this one? Well, let's find out. And this is what we're going to start from today. Okay, so just a recap to see what we were. So we have that. So I will actually, this is just a note, I will upload the lecture, a complete lecture, to complete, comprehending also the last lecture, so that you are going to have only one file encompassing the overall exercise. Okay, so it's simpler for you to have it. Okay, so nope. Let's see, nope. So we have that. Let's consider, for example, the deformation variable QF1. Okay, and we make this assumption that this variable, in fact, has an elastic part that we use with the subscript L, plus a rigid part, which we call D. So this is going to be our elastic part, and this instead is the rigid contribution. Why are we actually writing this? Please remember that when you take into account deformable bodies, as we have already introduced this problem, with the floating frame formulation, so you actually are not able to separate completely rigid motion of the body and deformation-induced displacements. Because basically, there can always be a relative motion between the frame and the body that deforms, because of course the local frame has to maintain its orientation between the mutual axis. It has to stay undeformed, while the body, by definition, has to deform. So the local frame cannot completely follow the deformation of the body. So there can be a relative motion, which is not a priori completely due to deformative processes. Okay, so in theory we say that okay, we can think that part of this coordinate is elastic and part is rigid. Okay, and the same, for example, goes in our example for the coordinate 4, so that you have a QF elastic plus the same quantity D. From a representation point of view, you have basically that this is your link. This is point A and this is point B, as you saw it. This is let's say the initial or reference or undeformed configuration. What I'm saying here is that you first undergo a rigid displacement D, which is the same for both. Okay, D. And then you have a deformation, properly said, which is QF1E. And here you have, for example, and this is in theory is different, QF4E. All right. So that, as you can see, if before our length was this one, before the deformation, now our length is this one. So that, in fact, a deformation has occurred. Now, if we want to write this down from a mathematical point of view, we have that the component 1 of the vector of deformation-induced displacement, so the axial ones, which is basically written as Q as psi1. So this is the first row, if you want. Is the first row of the matrix Psi. So it's the vector Psi1 applied over QF, by definition. And if you do it, since we have calculated, sorry, this is Psi, okay, you get QF1, 1 minus Xi, and this is E, plus QF4 E Xi plus D. Okay. So what I'm doing here is again just writing the axial displacements due to deformation. Okay. To do this, what I'm doing is multiplying by matrix multiplication the first row of the matrix Psi hat over hat times QF, where QF basically have been defined as previously done. Yes? QF is with the hat. Yeah, of course. Well, this one. Okay. So this is what I get. As you can see, we have a rigid part in this axial deformation, or in this component which u over bar 1 denotes the displacement induced by axial deformation. So it means that when you are going to basically write down the position of a point of our road, you get, as we know, R, which is the position of the origin, and then you have A applied over, as you can see, R0 over bar plus C times QF. Okay? As you can see now, it means that we have, and this is basically U. Let's try it like this. Sorry, so it's more evident. This is U. Okay, now it means that, as you can see here, you have a rigid component in U and a possible rigid component, a possible rigid motion in R, because R is the typical part of your position vector, which is describing the rigid translation of the origin, right? So this is the position of the local frame, remember, okay? So it means you have rigid contribution from U over hat and a rigid contribution of R from R. And you don't want it. You don't want this, okay? You want this actually to express only the deformation, the actual deformation. You don't want any rigid component to be here. Okay? So let's just denote it. So you have it here, as I was saying. But you also have it here. Okay? So all of this to say what? If you want to clarify your formulation so that the U over hat only denotes real deformations, you need to impose what? The so-called reference condition. Those are the conditions that we mentioned in one of past lecture to say that there is not anymore a unique relationship between the local frame and the deformation of the body. Because the body deforms and the local frame cannot follow. So the link must be established somehow. And when you establish it, you can do it arbitrarily. So there is more than one way to do so. And this allows to remove this rigid contribution. Okay? So let's do it. So we have to enforce reference conditions. How do we actually enforce these reference conditions? What we do is to basically consider our link AB as a simply supported beam. Okay? So we consider our body AB as a simply supported beam within our assembly. Okay, why a simply supported beam? Well, if you go and check again our picture, you see this is basically like a simply supported beam. Why? Because basically, if you consider your body within the assembly, so the relationship between the body and the assembly, you have that this one is a hinge. So it means that if you consider the body number 2 to be like typically your reference body, you have a rotation. This is a hinge, so you have a rotation, but there can be no relative motion, okay, between the two. All right? While from body, let's say 3 and body 4, you have what? You have a simply supported beam as well, because there can be only a rotation between the two, but the position between the two must be the same. Okay? So if you want to see the imposition of reference condition in another way, reference conditions are the conditions that you impose to your body, so to fulfill the links, the connections that exist between your body and the other bodies within your system of multiple bodies. Okay, this is what you're saying. When we will impose now our reference condition, we want to limit the possible displacements of our body due to the fact that our body is linked to other bodies. Okay? And so what we are going to write down now is what the condition so that at point A, body number 2 and body number 3 cannot only rotate relatively one to the other, but cannot undergo to relative displacements. And the same goes for body 3 and 4. Okay, so this is what reference conditions are. So let's do it. Our body is not just a single body, is not alone in our system, in our space, but is part of a system of bodies which are linked one to the other. And this is what we are going to take into account now. So we can represent our body to be like this. Okay, I will just, not to make it hyperstatic, okay, I will add the tray here, okay, but our reference condition will stay the same. So this is point A, and this is point B. So our link, our body, is exemplified as a simply supported beam. So what are the conditions that we need to implement? That the axial displacement at R0 equal to 0 must be 0. And the same goes for the transverse displacement. Okay? So the body cannot deform transversely or axially at point A. And then we have another condition so that the body at point L, the transverse also must be 0. All of this translates into what? That QF1, if you remember, this is the axial displacement induced by deformation at node A, must be 0. And then QF2, which is the transverse at point A, 0. And the axial at point B, which is QF5, is 0. All right? So these are the conditions that we have to implement. So, taking into account this, we can write a relationship between the overall vector of displacement of coordinates induced by deformation, so QF1, QF2, QF3, QF4, this is going to be longer, QF5, and QF6. With respect to the only one which are left. Which ones are left? QF3, QF4, and QF6. These are the only ones which are left. And we can say that this vector here is the same as writing this. 1, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, so 1. So what I'm saying here is that writing this here, imposing these reference conditions, and writing this relationship here between matrices is exactly the same thing. You see? Because if you consider this relationship between matrices, you actually are imposing this. Okay? So this and this are equivalent. Okay? They are equivalent. And this, in fact, is written as such. QF over hat, which is this one here. This is what we actually call QF. So these are the variable, the generalized coordinates associated to deformation, which actually can have values different from 0. And they are related to the QF over hat with a matrix which we call N over hat applied to QF. Okay? So all of this thing of the reference condition is a way, again, to enforce, to limit the capability of deformation of our body due to the fact that our body is connected to other bodies. So QF 1, 2, and 3, due to the fact that it is connected to other bodies, cannot have values different from 0. And a way to enforce this is actually writing this matrix equation here. And these are what they are called reference conditions. Okay, so these are the reference conditions. These are the reference conditions. Okay, actually, let's write it a little bit better. Okay, okay, so let's use it to the previous, let's say, equation that we have written here. Let's use this into this. Okay? And let's get eventually our psi. So we therefore have what? This psi to QF psi. This is what we had. But this is equal to what? To psi applied over N over hat applied over QF. This is equal to psi QF. Okay? And this is actually what we were looking for, our psi. So it follows that our psi matrix is psi over hat that we just derived last time, which is a 2 times 6 matrix. The N matrix that we developed before, if you go and check, is a 6 times 3. So it means that this is a 2 times 3 matrix. And in fact, yes, it makes sense because this is a vector which is a 2 times 1 vector. And this is a 3 times 1 vector. Okay? And if you go and do some math, you're going to get it like this. Okay, so this is our inertia. Sorry, this is our matrix of shape functions for our element. You finally got it. So if you want to represent the deformable body which behaves like a 1D Euler beam, which is constrained to other bodies in the ways we have seen, you have to use this psi. Okay, and this is actually what is going to Adams is going to calculate. Okay, so this is the first part. Now let's proceed further. Is it clear to you so far? Okay, so again, we cannot use the overall psi overhead matrix because the capability to deform of our body are limited by the fact that our body is linked to other bodies. This is the result. Okay? All right. Now, what we're going to do is to basically calculate the mass matrix, if I'm able to retrieve it. All right, so mass matrix. Okay, so in our definition, we defined it like this, as a series of submatrices. So we had M, R, R, we had M, R theta, and we had M, R, F, M, theta, theta, M, theta, F, and M, F, F. Okay, and of course here we have symmetric part. So what we're going to do is to calculate all of these submatrices in our case for our deformable body. Yeah? We can actually already see what are the dimensions that we can expect for these submatrices. So this is MRR. So the position vector of the origin of our local frame for body number 3 has dimension 2, right? So our R vector for our body number 3. Basically, it's in space, so it's just 2 coordinates. So I would say that this is pretty much a 2 times 2 submatrix, right? Then R theta, how many orientation variable do we have for a body in 2D space? I would say 1, right? Just like this. So this is going to be what? At 2 times 1, most probably. How about RF? Well, R is basically 2. We already saw it. And F, which is the subscript denoting deformation, well, we have just seen how many are the deformation coordinates that we need, which are left. 3, right? So it's going to be probably, oops, 2 times 3 submatrix. So 2 times 3. Here, as a consequence, it's going to be a 1 times 1, meaning that it is a scalar. Theta f is 1 times 3. And ff is going to be a 3 times 3. So all of these said, this is going to be 2, 2, and 2. It's a 6. Yes. Let me just 2 to 1. Just a second. 3, 6. Six times 6. Okay. All right, let's check this out. So 2 times 1, MRR. Okay. Well, this is pretty much always the same. It's M. I will not go through it. It's MM. Okay, it's constant. Where M is the mass of the body. And it's constant. And this we already anticipated, no? So this was super easy. Now 2.2. We have M R theta. Okay. So by definition, this was the integral of V of rho, the matrix B, and dV. Now this, in the 2D case, B can be written as the derivative of A with respect to theta times R. Okay, you can go and check this out also in the notes that we have written. It reduces to this. So we basically bring this out of the integral sign. What we get is the following. So we again separate R0 over bar, the V plus the psi. Oops. Okay, always in V. So I've written basically R over bar as the rigid part plus the deformation part. And then I brought out of the integral sign QF. Okay, that's what I did. So now, if you remember the definition, can I slide? If you remember the definition of the inertia shape integrals, because again, the inertia shape integrals are, again, those quantities that we calculate only once, and then we're done, to ease the updating of the mass matrix during our calculation, during our simulation. So if you remember, we define this R0 as the integral of ρ0 in the V. Huh? This is exactly the term that we have got so far. If we calculate it, in our case, this becomes rho A, where A is the cross-section of our beam, the integral from 0 to L, where L is the length of our body, of the vector R0 over bar. And R0 over bar, what is it? It's the vector composed like this. Why is it done like this? If you remember, we have basically, here I should have written R01 and R02. Did you remember? But I only write R0 because R2 is basically, if you remember, this is our link, and this is A and this is B. This is R0, the coordinate along the length, R01. And this is the length, the coordinate along the transverse direction, R02. But since this is a 1D model, and this we have already stated, the only independent coordinate which is left in our model is R01, and this is 0, identically 0, because it's a 1D element, okay? So instead of writing R01, I just rewrite R0 over bar. And R02 is 0, okay? This is why it's basically like this. And here we have the R0 over bar as a variable of integration. We can get out the following, R, A, L, and then we integrate basically on a non-dimensional, over the non-dimensional coordinate xi that we have already defined. Remember that xi, sorry, this is not xi, this is zeta. Zeta is R0 over by, divided by L. This is what we have defined. So, and if you do this, you get M L divided by 2 and 0. Why ML? Because this, what is this? The density times the cross-section times the length. So cross-section times length is the volume. Density times volume is the mass, right? This is the mass. And this is what you get. So this is the first inertial shape integral, you see? We got it. And then we need the second one. If you remember, we defined it like this. Rho psi in the V. And this is again exactly the second term that we are dealing with here. So again, let's calculate it. We have rho A, the interval from 0 to L of psi in the R0 over bar. We always bring out the L, so we have rho AL, which is our mass, as before, times the integral from 0 to 1 of psi in the zeta. And this becomes, if you take into account the psi matrix that we have just defined, this becomes 0, 6, 0, L, this is 6, 0, minus L, all of this being multiplied times M divided by 12. Okay? So you see, these are very simple integrals, but this is actually what happens in your code. So if this is true, and it is true, you get that S psi multiplied times QF is equal to M divided by 12 times 0, 6, 0, L 0 minus L times QF3, QF4, and QF6. Okay, the only three which are left. And this becomes M divided by 12, 6 QF4, and you have L times QF3 minus QF6. Okay? So we have to put what, this and this together, because you remember, this is where we were. A theta applied to this, and this is basically SR0. While this one is S psi. So now we have multiplied this times this. We have to add this and pre-multiply times A theta, and then we get it. Okay, so let's do it. So eventually we have that m r theta, which is A0, sorry, A theta applied to SR0 over bar plus S psi applied to QF becomes m over 12 applied to what? Minus 6 L plus QF4 times the sinus of theta minus L QF3 minus QF6 times the cosinus of theta. And then the second row is pretty much very similar. QF3 minus QF6, the sinus of theta. And as you can see, and as we have anticipated, is a 2 times 1 matrix. Oops. And this is linear in QF, but it's highly nonlinear in the theta. In rotations. Okay. Let's proceed further, and we have 2.3 M RF. This, by definition, is A times SC, if you remember. From the derivation, from the theory, we denoted it like this. And here we have everything. Okay, so let's just calculate it. Our A is just the cosinus of theta minus sinus of theta, sinus of theta, cosinus of theta. And this is A, the rotation matrix of a rigid body in the 2D case, times the second term that we have just derived, which was something of this sort. M times 12 applied to minus L sinus of theta, 6 cosinus of theta, L sinus of theta, L cosinus of theta, 6 sinus of theta, minus L cosinus of theta. And again, as expected, is a 2 times 3 matrix, which is nonlinear in theta. Okay. So you see, we are building step by step all the mass matrix. Let's move on. And now we have the following term, which is 2.4 m theta theta, if I remember correctly. Now this, by definition, is rho B transpose over B. Let's substitute, and then we get rho R over bar T, B transposed, sorry, not B transpose again, but A, T theta transposed applied over a theta applied over r over bar in the V. Now here for the orthonormality of orthogonality of A, this is basically the identity matrix. And this basically remains as the integral over V of rho R over bar transposed applied over R over bar. Okay? So we already can anticipate what is the dimension of this matrix. It's a scalar. This is a scalar product between two vectors. And in fact, we had anticipated it to be a scalar. Okay, so everything is coming back together. But we can simplify this, rewriting it into the three different terms, like this. Okay, basically I have unpacked R over bar into the constant part, the rigid part, and then the deformation. Okay, that's super, because you have that R is basically R0 plus U. This is always true. And then so we're going to define this term as m theta theta r, this term here as m theta theta rf, and this just, we are going to denote it like this arbitrarily because we are going now to get each single one of them separately. Okay, so m theta theta r is by definition rho a, the integral from 0 to L of what? R0, 0, applied to R0, 0 in the V. Okay? No, sorry, in the V, in the R0. And this is super simply ml to the third divided by 3 to the second, sorry, divided by 3. And this is the first. Okay, let's see the second. The second is m theta theta rf, which is rho a l, the integral from 0 to 1 to L xi, or zeta, sorry, times 0. What is this? This is basically our coordinate R0. This is R0, right? Zeta is R0 divided by L. So this is R0, okay? And then we have our U vector. So this is basically this is our R0 transposed, okay? While here we have 0, L times xi minus 2. Sorry, I say xi, but this is zeta. I keep on mistaking it. Zeta to the third. Zeta, 0. And then we have 0. L times zeta to the third minus zeta to the second. And this is basically QF3, QF4, and QF6. Okay, in the zeta. Why are we writing this? Because this here is psi, this is QF, and it means that this is our U. Okay, exactly what we were trying to write. Okay, we have all of it. If you do the calculation, you get M, L, the integral from 0 to 1 of zeta second, QF4, the zeta, and this is 1 over 3 M, L, QF4. And this is it. Okay. The last one of this is M theta theta F F. And this is rho A L, again, the integral from 0 to 1 of QF transposed over psi transposed over psi over QF in the zeta. Again, remember that this is U transposed, and this is U. Okay. So if you keep on going, you get, I spare you the math, but it's actually quite simple, M L squared over 105 QF 3 squared plus 1 over 3 QF 4 squared plus L over 105 L squared QF6 squared minus L squared over 70 applied to QF3 times QF6. I mean, the values are not actually quite, very important. It is important that you understand the process, okay? So now we have to put all of these three terms together to get M theta theta, which is a scalar. So we do it, and we get the following. RR plus M theta theta RF plus M theta theta FF is equal to M, which multiplies L squared over 3 plus 2/3 L QF4 plus L squared over 105 QF3 squared is 3 plus 1 over 3 of QF4 to the second plus L squared over 105 applied to QF6 squared minus L squared over 70 QF3 QF6. And again, as you can see, this is a 1 times 1 matrix, that's to say it's a scalar, and it's nonlinear in the Q's. Okay. Then we have m theta f, which is the integral by definition of b transposed over a applied over psi. Yes, I know. It's a little bit boring, but we have to do at least once, okay, to see what is actually the process in detail. RT, AT theta applied over A and psi. And this can be written as the integral over rho, R over bar transposed applied over, I will spare you the calculations, but it's 0, 1, minus 1, and 0. This is basically what you get when you apply A theta transposed over A times psi in the V. So if you do this, you get the following. M L over 30, L plus QF4, and this is the first column. Then you get M L divided by 60, three QF6 minus 2 QF3, and this is the second column, and then you get minus ML divided by 20 times L plus QF4. Okay? And again, as expected, this is a 3 times 1. Sorry, 1 times 3. Matrix. In this case, we have linear in QF. Okay. Last one. And then I promise it's going to be easier. Can I slide? Okay. (2.6), we have MFF, which by definition is rho psi transpose apply over psi. Did you remember this was supposed to be constant? It was supposed to be a constant submatrix. And in fact, if you calculate it, it's exactly constant, like this. L squared divided by 105, 0, minus L squared divided by 140, 0, L squared divided by 3, 0, and here you get, of course, it's symmetric, S squared divided by 140, 0, L squared divided by 105. This is the structural stiffness matrix. This is what you always have dealt with before actually taking into account rigid motions and so far. And this is constant. And it's a 3 times 3 matrix as expected. Okay. Now, so we have derived, first of all, the shape functions matrix, psi. Then we have derived the mass matrix. Okay, what are the other quantities that we need so to be able to completely define and to write down Newton-Euler's equations? We need the stiffness matrix, for example. Okay, so let's do it. Okay, so 3. This is easier. So we have that the strain energy can be defined as what? 1 over 2, the integral from 0 to L of what? Well, we have basically two ways that through which elastic energy can be accumulated in our body. Deformation through the axis, along the axis, and deformation transversely, so flexural deformation. So axial deformation and flexural deformation. So what is the typical expression for the axial deformation, for the axial energy, for the axial deformation energy? Is the axial rigidity, EA, times the second order derivative of the deformation of the first order derivative of the deformation along the axis. So it's what? It's U1 prime squared. Okay? This is what you typically, in your Euler beam model, write as okay. And this is actually what we have already seen in our 1D model, the one that we have imposed. And then we have the flexural counterpart, which is flexural rigidity, EI, times U. In this case, there are 2 times, always squared, integrated over the length of our why did I put this inside? Yeah, okay, let's go like this. Over the length of our axis, of our rod. So we perform this, and we get the following. If you do the calculation, you get integral from 0 to L. So this is basically a quadratic form that you can rewrite in such a way. U1 prime, U2 derived 2 times, applied over EA 0, 0, EI. In here, you write prime U2 derived 2 times. Okay? This is just the same, no? If you do this matrix multiplication, you get a scalar, which is on the upper row. Okay? Okay, can I slide? Okay, so nothing super complex so far. Now, let's calculate this one. This one is, as I was basically already introducing, is the derivative with respect to our x, with respect to our abscissa, which is R0 over bar, right? Of what? Of U1 over bar. But U1 over bar, what is it? It's the first row of the shape function matrix times QF. Okay, so this is U1. Okay, and if we do it, we get the following: D over dr0 over bar of what? Well, the first row of the matrix Psi is 0, R0 over bar over L, 0. Huh? You go and check the first row of the Psi matrix is exactly this one. And then you have QF. QF is kind of easy because it's QF3, QF4, and QF6. Okay, and then you have to derive all of this. Oops, sorry, this is super bad. And this is QF4 derived by L. Okay? The only R0 which is present here is this one. It's the only thing that survives. So when you multiply times this, you get this. So this is U1 over bar prime. So let's get now U2 over bar derived 2 times. Well, that's actually the same thing, not really different. So Psi 2 divided over QF. This is R0 minus 2 R0 squared divided by L plus R0 to the third divided by L squared. And this is the first column. Then you get 0. And then you get R0 divided by 3 over L squared minus R0 squared divided by L. And this must multiply. So this is the second row of the Psi matrix. QF3, QF4, QF6. And what you get, if you do this, so again, this is U2. Just to be clear, this is the second row of Psi. Okay? So if you do the calculation, you get the following. Minus 4 over L plus 6 over R0 over bar divided by L squared times QF3 plus 6 times R0 over L squared minus 2 over L multiplying QF6. Okay? So now you can write it down. Can I slide it? So now you have these two quantities. It means that you can get this one here. Okay? So it means that our U, our elastic energy, is 1 over 2 of what? QF3, QF4, and QF6 multiplying 4EI divided by L, 0, 2 times EI divided by L, 0, EI A divided by L, 0. 2 times EI divided by L, 0, for EI divided by L. Multiplying, again, QF3, QF4, and QF6. Okay? So we saw that U, so the elastic energy, could be written as 1 QF transpose times KFF times QF. Did you remember? This is one of the notes that we reminded from chapter 3 when we derived the elastic energy. Can you see any resemblance between this formula and the one that we got? They are basically the same. So it means that this matrix here that we have derived is KFF. So this is the structural stiffness matrix. Okay. Does it make sense? So first of all, it is symmetric, and this is already a relief. First. Second, is it actually correct? Can you actually guess if it's correct or not, somehow? Well, there are hints by which you can actually judge if this is correct or not. So for example, look at this one, this term here at the center. So it means that when you are going to basically extract your U, the one associated to QF4 is associated to this term of the stiffness. But what is it, QF4? Did you remember? So if this is your A and B, QF4, if I don't remember wrongly, is this one. It's the axial. While here you have that QF2 is 0, right? We have imposed it. So QF4 is actually the elongation of your beam, axial. Does this not remind you of the stiffness, the axial stiffness of your beam? Isn't it so? It is exactly that one. In fact, you have that EA, you can rewrite it as QF times L. What is it, this one? This is your epsilon x6. No? You see? It's the displacement, axial displacement, divided by the initial length. Huh? In fact, this is exactly your N, your axial force, you see? So it is actually correct that this term is written like this. It makes sense, okay? And the same goes also for these terms here, which are, of course, a little bit more complex because you have two different quantities associated to flexural deformation, so you want to have to save them, sum them. This is the only one associated to axial deformation, so you can judge it, right away. Okay. So it looks correct. So again, your KFF is exactly this one. 4 EI divided by L, 0. 2 EI divided by L. E A divided by L, 0, 0. 2 EI divided by L, 0. 2 EI divided by L. Okay, so this is the structural stiffness matrix, but what about, so this is the, again, let's actually write it down. Okay, but we didn't need the structural stiffness matrix. We need the structural matrix. Well, once you get KFF, getting K, as we saw, it's just super direct to do. Again, we saw that our U, which can be written as this, can also be written as Q, so all of it, transposed applied over K, applied over Q, with Q being basically what? R, theta, and then QF. And therefore, our K is just 0. Okay. So this is our stiffness matrix. All right. Now let's try to calculate one last contribution, if we are able to, if we have enough time. So again, if you remember, when we wrote the equation of motion, Newton-Euler equation of motion, we had the mass matrix, the stiffness matrix, and then what else did we have? External forces, QE. So let's try to get external forces as well, acting on this body. Let's do it. Come on. Wow. That's it. There are no more slides. Okay, let me just save it. I will compose it into one single PDF later on. Okay, so, but just too many slides. But to be fair, these are two lectures that we are joining together. So, but again, when we're gonna again run your simulation in Adams, there is basically maybe you will see it tomorrow. There is a command that you can basically, or a button, depends if you use the graphic user interface or if you go through script. But there is a command through which you basically start the simulation, in which you can actually assemble the system and then start the simulation. What does it mean? It means that Adams checks the compatibility of your constraints and your, for example, motions that you can impose and so on. So if you have done things properly, okay? This is the first checking that it does before actually starting the simulation. What it does during this checking moment is also writing down all of these matrices. Okay? All right. So, for external forces So if you have the vector of external force that we call Fe, let's actually see it again. Our system, which is basically done like this. So what are the forces here that we have insisting on our body number 3? External forces, not contact forces. What is the only force that we have? Yeah, so we have weight. And it acts basically. So here we are writing it in the inertial coordinate, right? So all of the weight is along the axis x2. So we have this, no? Just to be. So this is x1 and this is x2. So we have it, all of it in here. Minus mg transposed. Yeah? So this is x2. Okay, so it's the weight of this body number 3 which acts like this, in the opposite direction with respect to the vector x2. So what we do, or we start to do, or try to do, is to write the virtual work of external forces. If you remember the D'Alembert principle or theorem, could be written as such. Fe applied over the virtual displacement of which point? Where is the, exactly, center of mass is where the weight is actually applied, which we call PG. So this is our point G, center of mass. Okay. Where we have here that P let's write it like this. PG is R plus A applied over R, let's see, R over bar of point G. And in particular, R over bar of point G is made out of R0 over bar of point G plus UG over bar. Now, we have that R0G, what is it, R0G? In terms of coordinates? Well, I would say it's L divided by 2, 0. It's the position in the undeformed configuration of the center of mass. So it's L divided by 2 and 0 transposed. While UG, which is the displacement induced by deformation of the center of mass, what is it? Well, typically is it C, so the shape functions, the matrix of shape functions, times QF, right? But this is very general. So why is it G? Well, in these two terms, we have seen that the space dependence, is on Psi. It's not on QF. So I will rewrite it like so. Psi at zeta equal to 0.5 times QF. Okay? This is the deformation, the displacement induced by deformation of point G. Okay? So if we put everything back together, we have that delta PG is delta R, of course, plus delta A applied over RG over bar, plus A applied over delta RG. Okay? And this is again delta R plus A theta, because this is A basically depends only on rotation. So the only variation, even virtual, which we can have, depends only on theta. So we write A theta RG over delta theta. So here, basically, here I'm writing the following. What is it? Okay, this is what I'm writing. And then you get this one, this term here. Okay, I'm distributing it. And then, so let me cancel it out, otherwise it becomes difficult to read. Plus A times psi estimated at zeta equal to 0.5 times QF delta the QF. Okay? Allow me just a couple of minutes more and then we're done. We're done for today. So if we write all of this in terms of matrices, you get I A theta times RG A applied over psi estimated at zeta equal to 0.5 and then we have delta R, delta psi, delta Q on F. Okay, it's the same that we have written before. Okay, you see, if you multiply this times this, you get this one. If you multiply this times this, you get the second term. If you multiply this one times the last one, you get the last term. Okay, it's just a way of rewriting it, nothing different. So it means that delta WE, which is equal, as we have said, to FE transposed apply over delta PG, is equal to 0 minus mg applied over I A theta R0 Rg psi zeta equal to 0.5. All of this be multiplied times delta R, delta theta, delta Q on F. And this must be equal to what we have already seen. That's to say, QE transposed applied to R times delta R plus QE theta applied to delta theta. Okay, let me remove this because it's a scalar. Plus QE transposed F times delta QF. Okay? So basically, when you are going to multiply this times this, you're going to get this, basically. Huh? You see, if you put into evidence this vector here, you're going to get these ones. Huh? So it means, and then we're really done, that QE R transpose, what is it? It's basically this one, you see? It's this times this. Because then this part here must be multiplied times delta R. So according to this, it must be this one, you see? So this one here is 0 minus mg multiplied times I. This is QER. So this is the generalized external force associated to translation R. Then Q, we are just going to write it down this one, and then next time we will estimate it. This is what? 0 minus mg applied over a theta rg. Right? Okay. And then QEF transposed is the same, 0 minus mg applied to A and C, estimated at zeta equal to 0.5. So you see all those quantities which were appearing in our equation of motion can be calculated like this. So this is it for today. Oops. Next time, I'm not saying tomorrow, but next Monday is going to be 1st of May, so no class. So we're going to see each other for lecture on next Thursday. We will finish this exercise, basically calculating these quantities and then also analyzing the last thing that actually matters, which is the imposition of the constraints. Okay, because with this we are able to write down the equations of motion. We have mass matrix, we have stiffness matrix, we have the forces. The last thing which are left are the constraints. We will write it and then we're done. Okay, that's it for today.